thanks very much for inviting me. It's been a very interesting meeting. Condensed matter theorists should be the majority of the audience, so I've tried to sort of change the talk a little bit to sort of take that into account. So what I'll be talking about are the simulation of strongly correlated systems, and people have got comments on things that they think could be better simulated in this way, then I'd be welcome to hear them as well. So the basic idea, I mean, Emmanuel Bloch yesterday sort of talked about a similar sort of thing. The idea goes back, people say, to sort of Feynman, who sort of talked about the differences between a quantum system and a classical system. A quantum system's quite hard to simulate, and therefore, it's a good idea to simulate a quantum system with another quantum system. And the people doing quantum information processing often use this quote, but it obviously applies much more directly to what we're talking about in terms of making cold atoms behave like some condensed matter systems of interest. We've had a program on that, actually, funded by the European Science Foundation. European Science Foundation, which is just finished, actually. So the work I'll talk about here about rotating optical lattices, part of that, Emmanuel Bloch has done some work on fermions, which you didn't mention yesterday. It's theoretical work. We had a talk yesterday on disorder in lattices from Nikolai Prokofiev, and there's experimental work on that in Florence as part of this. And, well, I won't read this out, but the idea is basically to make the many-body systems look like strongly correlated systems. So what we essentially want to do is to make the Hamiltonian of our cold atom system look like that of the condensed matter system we want to look at. And one of the particular aspects that I'm going to talk about here is how we actually mimic or make an effect that's like having a magnetic field, which of course is very important in condensed matter physics. So I show first of all, so talk a bit about the background first of all, probably. That's possibly what most people are interested in here from a theoretical point of view. Describe how we can model then having a magnetic field, things that we could do if we could have that, which would be look at things like fractional quantum Hall effect states, antiferromagnets, and this is even a possibility. I'll actually then describe the details, perhaps not go into too much detail there for this particular audience, of things we've actually done, and then mention at the end something we've done more recently, which I think connects with stuff that Emil Lund has done in the past, and although he's talking later today, I don't think he's actually talking about that either, but just mention that. So. Okay, to start then, describe how rotation can mimic the effect of the magnetic field on a charged particle. So, in a very simple level, you can just look at the Lorentz force on a charged particle in a magnetic field, V cross B, and the Coriolis force in a rotating frame, so the frame rotating at omega, and the V cross omega looks like V cross B. So we make some sort of analogy here. The effect of the magnetic field QB would be twice the mass times the rotation. That would be just a simple-minded thing corresponding to some cyclotron frequency like this, which is twice the rotation frequency. That's a very classical argument. We wanted to actually, as I said, in these simulation experiments, actually make the Hamiltonians the same. So just do it more in terms of the Hamiltonians. In the rotating frame, we've got this modification, and we adopt the angular momentum, which comes in for the momentum term, and we go across R. And then if we have a harmonic trap, as we usually do in these experiments, this is the radial trapping frequency times R squared, and this is reduced by the central petal acceleration, the outward centrifugal term, if you like. So the faster we rotate, then that reduces the harmonic trapping. And comparing that to the usual substitution in a magnetic field with a vector potential, if we choose a particular gauge, this particular symmetric gauge here, then that looks like that. So what we want to do is to basically get rid of this term. So we want to rotate very, very close to the radial trapping frequency. So this term essentially cancels out, and then we'll be left with this and this, which obviously are analogous. And so we can look at the eigenstates of this system and learn something about the eigenstates of electrons, for example, in magnetic fields. And that's what we'd like to do. sorry, perhaps for this audience it's a bit simple-minded, but just to reiterate that point, explain how this looks like if we're applying it to a 2D harmonic oscillator with axial symmetry. So here are the energy levels of the harmonic oscillator. Here, this is the Z component of angular momentum, mz. So we've got 0, plus 1, minus 1, and so on. And if we rotate, then the co-rotating terms look like they're rotating less fast and go down in energy. These go up in energy. So what actually happens if we've got this, then here's our harmonic oscillator. And if we rotate, these come down in energy and these go up in energy. So, like that. Again. So as we rotate, so that the rotation comes up to the trapping frequency, essentially we cause these levels here, the co-rotating ones, all come down to be degenerate. And this is then analogous to having Landau levels with the separation twice the original separation, just like we showed at the beginning. That's essentially what we're trying, the trick we're using to try and model the effect of the magnetic field on our cold atoms. With our cold atoms, I should say. So, what do we want to do with that? Well, and how close to this trapping frequency do we need to come? That's the issue. We can't go there exactly, otherwise the atoms will disappear from the trap. Basically, we want to make these levels degenerate enough so the interactions mix them, and they're no longer single particle levels, but we consider them as the strongly correlated states. And that turns out, I won't go through the nitty-gritty of the details here, but there's some formulae that you can work out how close to the trapping frequency you need to be, or in terms of the number of atoms, or actually just at the bottom turn that round. So this is, if we assume that the difference between the trapping frequency and the rotation divided by that is 0.5%. In other words, we've got up to 0.995 of the trapping frequency, and we want to get to a filling fraction, which I'll define next, but it's basically the filling fraction you're familiar with in the fractional quantum Hall effect. To see these effects you want once around 1. Then the sort of numbers you're looking at, unfortunately, are rather low, about 40 or 45 atoms, depending on whether you have a low or a high trapping frequency, and quite low temperatures. But as Manuel was showing yesterday, we can now, well, one in principle can now detect single atoms, and so these are sort of feasible numbers to work with, and that would be where we're trying to get to. And if we can do that, then we can realise this goal that was first proposed by Mike Gunn and Nicola Wilkin and Nigel Cooper in Birmingham quite a long while ago, to actually look at the states that are analogous to those you find in the fractional quantum Hall effect by looking at fast rotation frequencies. And this has been nicely reviewed recently by Nigel Cooper, who's now at Cambridge and has continued to work on this. And there's kind of a lot of interesting physics in that, but the experiments have actually got to get to the point where we can do these things. I think Suzanne Weifers, is that how you pronounce it here, also worked Weifers? She's also got a review on this. So that's the sort of general idea. What are the sorts of things that we can do? There's a whole host of things in this review. Well, first of all, just define what we mean by filling factor. I think people, in the fractional quantum Hall effect, that's the number of sort of flux quanta per particle. Here it actually is equivalent to the number of atoms per vortex. So in fact, if we actually want to get into this highly correlated state, we've actually got to get essentially the number of vortices and the number of atoms comparable, which is why it's rather hard to do if you have a large number of atoms. So that's why if we work with sort of tens of atoms, then it might be feasible. And if one can do that, then there's, and probably the people in the room are condensed matter theorists are more familiar with these states than me. You might wonder whether I've labelled these wrongly, but these are in terms of the filling fraction, because this should be a third if it's a fermion. But here we're talking about the bosonic analogues of those states, so they all come out at different fractions. But nonetheless, Nigel Cooper and Charlotte has shown that the physics is very much the same. And obviously, although it would be good to see this state, these are perhaps the more exotic ones that condensed matter theorists are most interested in. And obviously, if you could, like Emmanuel showed yesterday, actually take an image where you saw all the individual atoms and within such a state and looked at the correlations, that would be very interesting. mentioned, there has been a preprint very recently where these authors, Nathan Gumelka and Stephen Chu, have reported that they've actually got the system into the fractional quantum Hall regime. Perhaps I won't say too much about my experiment, but basically that was an optical lattice of a collection of lots of copies of about 4 or 5 atoms, which they then individually rotated. So, I mean, that is actually quite close to getting into this regime. Okay, so, again, this is probably something that people are familiar with. It's just to show that the effect of putting in a magnetic field when you make this substitution. Actually, maybe I think I wrote it on the board, it's easier. Basically, in the momentum operator, if you make that substitution, then obviously that introduces, so this is the vector potential now, that introduces some sort of phase factor here. So the effect of having a magnetic field, when you translate the wave function, comes down to this additional phase factor here. Or if you actually go around a loop, integrate magnetic potential around the loop, that's actual flux around the loop. And well, this phase factor here is going to be important, this changing phase of the wave function when you either rotate it or you apply a magnetic field is going to be important. What it actually introduces then, if you actually have this Bose-Hubbard model, which we've seen already several times in previous talks, for the hopping between, I've actually written it two-dimensionally here, so it's just hopping something that was in P minus 1Q and ends up in PQ. The hopping term here acquires this Piles phase factor here if you have a magnetic field, or equivalently in our experiments if you actually do rotation. So these phase factors here then add up in certain ways as you go around, say, a loop. So one can actually then, when you've got rotation, as say, these phase factors come in, just as if when you piles obviously originally considered the magnetic field, it's the same thing. And if one actually then makes it such that the phase factor is at pi, on going around some plaquette in your lattice, you end up with a frustrated system. Because obviously you can't have, these represent the phase at each point, you can't get phase shift of pi to add up as you go around. Here I've drawn pi by 4 between all of them, except then you're left over with, you can't fulfill it here. So this is a standard frustrated system again. People are familiar with that. Or perhaps even more familiar with this example, which is the sort of, in terms of a phase shift, it would be, you'd have a triangle with 3 phases here. So if these have a pi phase shift, now if you want to pi around the loop, then you'd want the 3 to be have no phase shift relative to 1 or 2, which clearly you can't achieve. And that's analogous to having the antiferromagnetic frustration that people are familiar with. And so there's actually, that's what I was just going to point out now, there is actually quite a nice mapping between the states of bosons on a lattice and antiferromagnetic systems, which then we can actually use to model antiferromagnets. So I actually draw it up in ARIA, I've put it up here before. So basically, if we have the Bose-Hubbard model, I and J, just go for a one-dimensional case now. So that's the standard tunneling. Sorry, I think J is, most condensed matter people use T, don't they? Well, J is the same as T. So, unfortunately, my slides are in J, so I've just kept the J here. So that's the hopping term there. If we now map that onto a spin-a-half system so that if the occupation is 1, that's spin up, occupation is down 0, spin down. Equivalently then, the creation operator is that sigma minus, the annihilation operator is sigma minus, the creation operator is sigma plus. Then we can see that this ordinary Bose-Hubbard term for the hopping here maps onto this in terms of the plus and minuses, which trivial rearrangement becomes sigma x, with the 2 adjacent sides, sigma y, which I think is. So basically this is a magnetic interaction, obviously, so which the energy scale, the interaction term between them, is actually the tunneling matrix element. And that's actually quite interesting, because with bosons you've actually got a reasonably high energy scale here, with some of the systems that people have talked about with trying to model things with fermions, then you get an energy scale that's related to J squared over U, which if JMU is quite small, is itself quite small. So here we can actually, this frustration I was talking about in terms of phases before, the fact that it's difficult to, you can't get pi around here, is then you can think of it in just as in antiferromagnets. If these are anti-parallel, then this one can't be anti-parallel to both of them. It's exactly the same frustration coming from exactly the same way, and therefore we can actually use this system to actually model a frustrated antiferromagnet, which obviously would be an interesting system to look at for things like spin liquids and so on. Oh yes, that was. I was a bit ahead of myself there. So there are, just choose an example of something that people in theoretical physics in Oxford looked at, then these sort of systems which have triangular lattices with antiferromagnetic interactions are known to have frustration and interesting states. So maybe that's something that we can do with cold atoms as well. Okay. An even more exotic one here, perhaps a bit fanciful, but you can play around on the computer and you can show that if you take it's just a graphic produced on the computer by playing around with a triangular lattice, which is the blue one, and then there's a triangular lattice of twice the period, which basically pushes the atom, so it stops atoms being on these states. So if you look at the red ones, they're actually also a triangular lattice of twice the period, which basically block out these particular sites, and what's left is a sort of hexagonal lattice like that. So, I mean, with cold atoms, one can weight that with optical laser beams, and that would be an interesting system as well for studying frustration. Okay. So, what I've shown so far, basically, I've already described this. And what's important then is really the phase that goes round, going round the loop. And just introduce this parameter alpha, which is actually the fraction of 2 pi that phase is. That would be more sort of useful in. So if we've got a lattice of side D, then before we had a phase of pi, that would alpha would be a half. And so this just introduce that for the following. So in terms of the Hofstadter butterfly, that alpha, which was the phase before, would actually be the flux through a plaquette, the magnetic field times the area of it, divided by the elementary flux quantum. And the interesting regions are, I mean, if you plot this out, this is alpha essentially from up to a half. This is an interesting region. Corresponds to effectively really high fields. And we could actually reach, I mean, those values of alpha, which as I say correspond to around pi around the loop. And that's which are equivalent in sort of condensed matter or solid state systems where D is quite small to very high B fields. But in an optical lattice, the size of the plaquettes is quite large, so in this regime is actually accessible. That's another thing that one can actually try to do. So this would be actually not copying something that's done in condensed matter. You actually access a region where you couldn't get to, perhaps, in other ways, and that's another interesting. So those are just some of the things that one might think of doing with a rotating system if you can essentially apply a very high magnetic field. I think now I'm just going to turn to describing a little bit about our experiments and how we actually do this in practice. Okay. So, just to sort of give the background, rotating lattices have been made by other people before we did any work on this. There was an experiment at Giller, in Eric Cornell's group, where he made a rotating lattice like this, took a laser beam, and he had a mask, i.e. sort of a blank plate with 4 holes in it, so that the laser beam was fixed, but the mask was rotating. So you actually create 4 beams that are rotating. Admittedly, very little of the light comes through, but enough comes through that when you put it through a lens and it interferes, you create a lattice that's rotating. And they use that in their experiments on rotating condensates that were already formed. So if you have, this is actually, these are pictures from Giller, so you have a BC that's already formed with a vortex lattice in it. If you impose this rotating lattice, you can actually change from a triangular shape, if you look at it, to a square shape. So it's slightly unfortunate that it's at 45 degrees, this picture. If it was vertical, then it would be easy to see, but these are actually squares here, whereas these are triangles. So that's one thing that one can do with a rotating lattice. Is this vortex pinning, which comes, you only need a very weak lattice to actually just pin the vortices and shift them or rearrange the lattice. If we actually wanted to do fractional quantum Hall effect physics I was talking about before, then we'd actually need a deep rotating lattice with really, in the regime, with just a small number of atoms. We haven't actually got there yet, but what we've actually made is a much deeper rotating lattice than previously, much larger than the chemical potential, but still with a fairly large number of atoms per side. And that's what I was going to... just before I talk about our work, I should also mention, just to sort of for completeness, that instead of actually rotating the atoms, there's a method where you can sort of directly produce a vector potential A by some sort of Raman transition type arrangement, which has been pursued at NIST, and they've actually, I mean, it does produce an effective rotation as in their images when they're not rotating it, but they put on this Raman potential and release it and actually see vortices. So that's also an interesting route, partly because I think it allows you to access non-abelian fields. That's just really for completeness to mention that is also going on. So they also quite interested in looking at fractional quantum effect physics in that, quantum Hall effect physics. Okay, so how do we do the rotation in our experiment? As I say, I won't go through too many details because most people here aren't experimentalists. Do something about it. Essentially, they look something like this. We have our glass cell with the UHV containing the cold atoms here, and the laser light coming in from all directions, 4 directions like this, and crossing over, so that interference creates our lattice somewhere there. And how we rotate that is the following. We actually have a system where we have a laser beam which is deflected both in the x and the y direction, and we can vary those sinusoidally and cosinusoidally. So it's fairly straightforward to, well, with a lens here, to produce a beam that's moving around in a circle. That's a standard optical element that one can basically buy. So to turn that into a pair of beams, you use something that's basically like a microscope interferometer. So here's a beam splitter. This beam comes back out, whereas this one is split off and goes the other way to a retroreflector like this with a lens with a mirror, so that it comes back parallel to where it went in, but displaced on the opposite side of the optical axis. So that comes out here. So what that arrangement does for you is essentially you've got one beam going in, and it creates a mirror image of it on the other side of the optical axis. So when one moves around, it follows it around like that, where if one moves in, it just stays exactly the same distance and 180 degrees out of phase around the optical axis. So that's how we create the two beams, which then, if we put a lens in, interfere to produce interference fringes like this, and as these rotate round, and these rotate. So we actually have created a set of fringes in that plane, perpendicular to the board. And the advantage is, sorry, probably not so relevant here, but I mean, it is actually much smoother than the mechanical method and can go to quite high frequencies. And you can just sort of start off from 0 and ramp it up or change the frequency as you want, because there's nothing mechanical with any moment of inertia in there. I mean, if you actually got something spinning at several kilohertz, you can't really just stop and start it immediately.
You mentioned that the GLI experiment had some heating. If this was too deep, I mean, is this the way to go around it? Or?
Yes, well, we get less heating, but we got much less heating than they did because we can get a deep lattice which doesn't heat the atoms. But there's still a certain amount of heating. Yes. So yes, it does get round that. Yes.
But yeah, so I mean, you can go now that your lattice is deeper than the chemical potential.
Yeah, without heating them too much, as you'll see in a minute. Yeah. I mean, I think our system, the actual optical part of this part of it is fine. I think if we actually need to work probably on making the optics a lot better if we wanted to go a lot further. But yes, it seems to work quite well. So if we do that twice, so that we get, so we just got two setups, and we bring the beams together, so one pair creates fringes like that. These ones are out of, in quadrature with those 90 degrees, and that is our two-dimensional rotating lattice then, that we can actually load atoms into. So that's a picture of the laser beams themselves. Very interesting. And then we, well, skip over that perhaps. We just have a sheet of light in this direction to make everything two-dimensional.
What's the spacing, the lattice spacing between that?
It's around 2 microns. That's, yeah, I'll come back to that in a second. Okay. So as I mentioned before, what's important here is this phase around the loop. And in our experiment, what we actually have is a large number of atoms at each site. So instead of using the Bose-Hubbard model, really want to think in terms of going towards sort of number states with a well-defined phase. So we haven't really got individual atoms at each point. We've got BCs, and so they have it's really now become equivalent to a set of coupled Josephson junctions, really, rather than which obviously the Bose-Hubbard model is underlying that. But here we actually got a large number, so we've got a well-defined phase at each point. And the Hamiltonian that would describe that in this large number limit then would be this. I didn't complete this. That's actually our system. As I say, it's essentially then what we see is that this is actually a picture of the atoms in absorption. So it is, as I said, just a large number of atoms rather than the individual atoms that the manual showed, and that is equivalent to a Josephson junction array. Okay. And when we rotate and release the atoms, then we see something like this. This is the rotation frequency here of the lattice. So we start static, rotate it up, and then reduce the lattice and allow the atoms to expand. We see that vortices are created here, even at very low rotation frequencies. Or if we have a weak lattice, in fact, we don't see that. So I'll come back to that in a second. So this basically, as you expect, as you rotate faster, you create more and more vortices. There's no hysteresis here. We seem to be winding up the phase just proportional to the rotation rate. So it's slightly different to previous methods that have been used. And if you plot out the number of vortices here versus the rotation rate, well, it's linear as you expect from the superfluid trying to mimic the rigid body motion. So basically that's just the area and then the number of vortices can be worked out from that. And it does expand slightly as it rotates, so just take that into account. There is a slight difference between the weak and the strong lattices if one looks carefully at this first region. Here, that if we have a deep lattice, basically we rotate things and the phase winds up exactly proportional to the rotation rate. If we have a shallow lattice, so that the atoms are sort of not being carried around, as it were, it's actually much more like the previous experiments where people have actually stirred the condensate to actually create vortices. And we'll see that that doesn't work up to a certain threshold frequency. So here, we're actually basically putting that phase around the loop directly on the atoms, whereas here, it's sort of stirring up the system. And you can see that again over here, that if you have a sort of fixed, you look at the rotation frequency where you first see vortices, then if you've got a weak lattice, which is, this is the depth here, and this is the minimum frequency to see a vortex. If you've got a shallow depth, you've got to sort of go quite high frequency, stir it. But when you've got a high depth, then basically you see vortices as soon as you rotate at any frequency, just 1 hertz is the lowest we actually measure. And that then is well known already. In fact, the reason for that, if you actually look at the vortex nucleation and the energetics of it, then here's the energy as a function of the radius. So there's the energy to have a vortex as a function of the radius. And so for different rotation speeds. So if you're not rotating, then vortex is energetically unstable. You can create one, but it would tend to want to come out of the EC. Or if you create one out here, obviously, which you might do with stirring, it's not actually going to penetrate into the EC. But as you go faster and faster, then the energy comes down to a certain critical value, where the energy here is the same here. So if you create a vortex here by stirring, it will want to actually come in. And if you actually rotate faster, then obviously it's more favourable for the vortex to come in. This has been studied already, but the point is that this minimum critical frequency here for our case is the 4 Hertz that I showed before. If you rotate less than that, then when you stir, the vortices don't actually penetrate into the system. So that would explain why we actually have to, when we're, as it were, stirring in the shallow lattice, have to go above a certain speed before we see anything. Okay. I think I've already talked a bit about that in terms of modelling the magnetism. And just compare it with the case I've just been discussing. Here we've got frustration of a pi phase shift. If we actually rotate so that we have a 2 pi phase shift, then now we can satisfy that condition everywhere. So if you look at these arrows here, then there's pi and pi on this bond. So we can have 2 pi around each of these loops. You can actually get to a point where you've got a vortex actually formed with each one. Okay, so actually the point I wanted to make there was that that's one case, but you could also, even in our case, also rotate so that you actually have frustration. You have the case of a pi phase shift. So that would be a frustrated set of Josephson junction arrays, which actually being modelled by this chap in Japan. So he did the calculations basically. Unfortunately, he's used F, which is the same as alpha, in fact, sorry. Change the rotation there. So this will correspond to, so if we had F was 1, we just have a vortex at every plaquette. So these are the atoms here. We'd have a 2 pi phase shift. Here we've got a pi phase shift. So you sort of get one vortex for every other lattice site. And obviously then there are 2 possible configurations. You can either choose to have the vortex here and tends to line up like that, or if you shifted these over one period, you get exactly the same pattern with exactly the same energy. So that's in some sense where the frustration is. I mean, there's several identical, when I say identical, they look at the same pattern but just shifted over states with the same energy. And the system's got to choose between them. So we actually looked for this in our system. But unfortunately what happened was we didn't really see these regular rays. And if you look at the theoretical calculations as a function here of the alpha or F as you got, you can see that the energy of these states has sort of minima like this, but they're actually relatively shallow. And it seems that any slight perturbation will kick the system out of these. And maybe in some sense it can be slightly glassy as well, and that in practice the experimental system finds it hard to find this configuration when you actually rotate at these particular values. But nonetheless, we can get to the experimental conditions where we will be able to see that. Okay, one final thing I wanted to mention on the experiment, I think sort of a bit related to what Emmanuel was saying yesterday, but obviously people want to make a microscope to image the individual atoms. And I think, well, you asked the question about how small a lattice spacing you make, and we're here making our lattice by sending the laser light through the lens, so we're limited by the numerical aperture. In fact, if you remember basic optics, here the minimum spacing here is just lambda over 2 sine theta, where theta is this angle, which is the numerical aperture, and that gives us a, if we actually had a numerical aperture of 0.7, that would be about lambda over root 2. And this is exactly then also basically the condition for resolving the sites as well. If you actually think about having an object that has this sort of spacing on it and send light onto it, these are the diffraction orders, and whether they go through the lens and are collected, that determines whether you can see that. So basically, if we have light forming a lattice like this, the spacing will be about the minimum spacing that the lens could resolve anyway. But what we can do with our setup, and again, there was a mechanical version of this somewhere else, we can actually take the laser light and change it to expand the lattice. So it just helps if you actually want to resolve things. If you don't have such a good lens as they do in Munich, we've actually demonstrated we can't actually resolve these atoms in our systems because they're 2 microns apart. If we expand them using that trick, we can actually get 5 microns apart. And we can actually then switch it so that we expand again from this situation to make them 14 microns apart. So again, these are many atoms here imaged by absorption, but one can actually sort of magnify the image in this way. And I mean, this might be useful in what Emmanuel Bloch mentioned at the end there. If you had more than one atom per site, and you wanted to sort of expand it out and then put it onto a finer lattice, you might divide the atoms up between the different lattice sites so that one would could see that. So if you expanded it out and then switch back on the finer lattice, then those atoms in one well here would be now divided up between the original wells. That was the purpose of that. I mean, in fact, in some sense, it was a bit of a byproduct from what we realised we could do that with our particular setup. It was a nice demonstration. Okay. So finally, I wanted to come to something that I put in just at the last minute a bit to do with rotation so it's related to rotation, but not necessarily to optical lattices. It's really an experiment that we did where we set up a trap that has a non-quadratic potential, so that when we rotate in that, we can actually see some sort of interesting phenomena. As I showed in the previous part of the talk, as you rotate up to the trapping frequency, when you get to the trapping frequency, the atoms will fly out. But if you have say, a quartic potential, a higher order term in your potential, then when you've cancelled out the quadratic term, you're still left with some weak trapping, and that's quite interesting. So what we actually did was to use this method proposed quite a while ago by Garraway and Zobe, but you trap the atoms now actually where the radio frequency radiation is highest, which I think it was that rather put a lot of experimental people off, because they were used in cold atoms to actually using the radio frequency radiation to remove atoms. And the idea that you would actually trap atoms where they were strongly interacting with the RF was pretty counterintuitive. But really it's rather straightforward in the sort of dressed atom picture, and it does seem to work quite well. So basically we have our magnetic trap. So this is around the magnetic field minimum here. So this is the field as a function of the radius, say, r here. And these are the 3 hyperfine states, say, of the rubidium atom, which most people use. So the MF equals -1 is the one that is trapped, so it has the lowest energy in the lowest field, and higher energy as you go out. This one obviously has very little Zeeman shift, and this one is anti-trapped. So that's a typical, say, in the bottom of these Yoffé traps and so on that people commonly use. That's what you'd have. And there's this is difference here corresponds to the Zeeman shift for the bias field. So if we apply a radio frequency radiation to this, then we obviously interact with atoms at this position here and this position here. And in the dressed atom picture, you can model that by shifting these potentials up. In fact, I just draw 2 levels, but in fact it's very straightforward to do it with 3. shift this level up so that it's into now a sort of DC picture. This is now interacting here, and there's an avoided crossing. So essentially you change the, this is just a picture of how to model it, but basically you change from this, and where these interact, the potential is changed, so that instead of continuing up down there, it's an avoided crossing that goes up here. So essentially from this, you create this potential in the dressed atom picture. And it turns out then that atoms are now shifted to these minima here, as I said, at the points where they interact most strongly with the radio frequency radiation. And it turns out if this radiation is actually strong enough, the Landau-Zenner probability for making transitions is very small, and the lifetime for trapping atoms here could be many seconds. And what's the advantage of doing that? It's just a sort of, is it just a fancy trick, or does it get us something? Well, it enables us to sort of make some quite interesting potentials. So, for example, if we take a 2D slice of a Joffé trap, then basically the atoms will interact at this point here, some sort of at some radial distance. So we immediately create some sort of ring-shaped potential like that. Or in fact, if you look in 3 dimensions, they're actually trapped over sort of the surface of an ellipsoid around the magnetic field 0. And the relevance to the talk here is that we've actually, well, we've done this and loaded atoms into these traps, as reported here. But the relevance here is that if we now think about this in 3 dimensions, so as I said, if we have a sort of quadrupole trap, it's the surface of some sort of ellipsoid, and with gravity the atoms will then be trapped down here. And if you now look at the trapping potential, it's now harmonic, as most things are near the bottom. But as we go up here, instead of just being harmonic, it's actually become much steeper here if we follow around this ellipse. Obviously it's become vertical here and folded back on itself. So its curvature must be much greater, or a little bit greater I should say, than quadratic. So we've actually got some quartic term. And so the advantage there would be that we can rotate now, so we cancel out this term completely, and we're still left with some trapping. So what will actually happen is the atoms will actually fly out, but not go all the way, just disappear to infinity, because the trapping gets steeper out here. They'll actually go out into some sort of ring. And so that will be sort of very helpful in some of these rotation experiments.
Can I just ask, should we visualise this as being trapped on a 2D ellipse, which is vertical oriented, or onto an ellipsoidal shell?
Yes, it's a shell.
It's a shell.
It's an ellipsoid, it's a 3D ellipsoidal shell.
Okay.
Well, I mean, you could visualise it as a sphere, I suppose. Squashing is a bit irrelevant here. But there are subtleties to that. That assumes that the coupling to the radio frequency is constant all the way around, actually, because the polarisation changes. It all changes things slightly subtly.
So do you find losses in particular regions?
Yes, but we make it at the top, in fact.
Okay.
So if you've got circularly polarised radio frequency, which keeps everything nice and symmetric, the coupling is strong here, and then it just dies off to 0 up here. So, but that's all right.
It's more of a golf shapes trap.
Well,
you couldn't think of spinning the atoms around the shell, for example, because you lose them.
Well, you can, yes. I mean, if basically as you spin it up faster and faster, then they come to the equator, won't they? They won't go up here as you actually span it right out. They'd eventually settle down to a big ring going around the equator. I mean, there's a lot.
Experiments with the ring geometry.
Yes.
When it's not a shell, but it's ring.
Yes, we did that with a ring. I mean, the ring, that actually was from an earlier talk. We did some experiments where we actually had 2 sheets of light. So we confined the atom to a plane. And then we sort of took a cross-section through the ellipse. And that was a ring. And so, you know, then you're going to say, well, why don't you study persistent currents and things like that?
I was hinting at a slightly different thing. Did you find them rotating most of the time without any specific rotation? You don't rotate anything, they just end up rotating by themselves.
Yeah. No, we didn't look at that. You mean just sort of evaporate into that frame and
And they will rotate.
Yes. I think people have done those experiments now.
I don't know.
People, Brian Anderson at Arizona has done various things like that, where he's not quite the rotation in a torus, but taking several disconnected BCs and joining them together and showing that they're spontaneously vortices there. Is that the sort of thing? Right. Okay. Well.
Hi, did you study the persistent current in the ring? No.
Not yet, no. We'd like to do that, but we haven't done that yet. I mean, the history of it is we sort of, as I said, we loaded atoms into this. We actually did it with 2 sheets of light, so we actually made a ring trap. But there were some sort of technical things about, I mean, it's always difficult to get a laser beam exactly aligned with a magnetic trap, and it sort of drifts with time and so on. So we actually much prefer this new method that we've got, where we don't have any laser light, we just do everything with the RF plus magnetic trap, because in some sense they're always permanently aligned with each other. So that's persistent currents is something that we might do soon. And this will be actually a very smooth potential. So there might be some things that one would consider doing, such as well, just persistent currents, but also rotating up close to the speed of sound, because it's a very smooth potential. And I think you might actually, I'm quite sure that you might even be able to go beyond the speed of sound without too much problem if there was no irregularities to actually nucleate any vortices. I mean, that's one direction we've definitely thought about, we haven't got to that yet. I mean, what we're really focusing on in the shorter term is to use this for the fractional quantum Hall effect type work, not in a rotating lattice, but just with a small number of atoms here that are rotated up, perhaps just slightly beyond this trapping frequency, so that they're just out here in a sort of ring that might come back, and form fractional quantum Hall effect states here. Okay. But the thing I wanted to mention was the connection with, as I said before, you can actually get, even if you don't talk about fractional quantum Hall effect things, in these anharmonic traps, some quite interesting combinations where now multiply charged vortices, i.e. ones with double circulation, actually become stable. And I think Emil has sort of simulated this and various other things over the years that one might want to look at with such anharmonic traps. I think, well, we've had a bit of discussion on this. This actually corresponds to also a fairly small number of atoms in the trap, fairly low sort of interaction strengths. Again, that might be a difficult regime to access, but probably possible. So it does change the physics of things. Okay, so I think that's more or less all I was going to cover. I'd be happy to answer questions. Let me just summarise them. So basically I've been through the 2-dimensional lattices, shown that you can model the effect of having a magnetic field on the equivalent condensed matter system. And we've looked at the deep rotating lattice and the 2D accordion lattice, and various other things hopefully in the future. We can therefore perhaps look at, with the accordion lattice, strongly correlated states, the antiferromagnets, and frustration, which obviously is an important thing in various aspects of condensed matter, and this fractional quantum Hall effect physics, either outside an optical lattice or eventually in an optical lattice, will also be extremely interesting. Okay, so just to thank the people, Ross Williams, and who's actually often missed to work with a group over there, it's not quite well, within the general area of Bill Phillips's work, and Sarah Alassane, who've done most of this work on the rotating lattice in Oxford. Okay, thank you.
You
mentioned that you have this array of Josephson junctions, and you mentioned that the energy differences between these different states was somewhat small, and therefore it was hard for you to see some orderings that this Japanese guy had computed. So I mean, is it totally unfeasible for you to somehow do the cooling while you are rotating? I mean, is that impossible? Because I was imagining that, I mean if you start from a condensate and then disturb it, then it somehow, I mean, then you create other excitations, and it's hard to see these small energy differences, but if the system can find its own minimum energy configuration, then maybe more sensitive.
Well, there is one problem. I mean, they can evaporate when we're rotating, but I mean, basically, when the atoms are deep within the lattice, then they just can't get out. So in our particular method, once we've actually got a deep lattice, then the atoms can't really escape. And I mean, perhaps I should have emphasised that more. That those pictures I showed of the clouds after they've been rotating. There was a BEC that was put in the lattice, rotated up, and then released, and it was still essentially more or less quite a large fraction of it was Bose-Kins ends. So through that process, we haven't heated them, but that's the main experimental difficulty that took a lot of time and effort to achieve, is actually putting them in the lattice and rotating them without much heating. But there is obviously a certain especially as you go to very high rotation frequencies, I think. Where is it? Yeah, sort of. Lost it again. But the very high rotation frequencies obviously is heated up a bit. Here we got very clean signals. It just gets a bit hotter when you're actually getting up to near the edge here. And in fact, you can actually go slightly beyond 1. We didn't keep the data on there. But actually, once it's in the lattice, then the lattice stops it flying out. So the data out here is quite messy. I mean, there might be a way of cooling it if we've got a 2D lattice, to actually cool it from the sort of other direction, so allow the atoms to escape. If we had, say, a Bluetooth lattice that didn't confine them, just to extract energy that way, but was different to our particular setup.
So how close are you to these quantum Hall regimes then? When you rotate that part? I mean, I don't understand the connection yet. When you're in the harmonic graph, the number of particles and the number of voices, that's a regime you want to be in to look at this quantum Hall physics. But in the lattice, I mean, you say, well, you're basically there, right? I mean, you're at omega close to omega 1. And the rotation is 1. So how close are you to the...
No, I think it is different. I mean, we'd actually need to, this is a sort of different regime altogether. We'd really need to be doing this in the regime of, just because the interaction here is huge. You really need just a very few particles per lattice site. And then we would be in a quantum Hall regime. We've got hundreds per lattice site here. So the interaction strength is essentially leading to a Bose condensate at each site, whereas the fractional quantum Hall effect states would be more sort of the individual atoms sort of hopping through.
But now you're thinking about quantum Hall states on a lattice site. Or you're thinking about...
Oh, not on a lattice. Yeah, no, I wasn't. No, that's the Stanford experiment. Right. Doing it on... Yeah, probably I wasn't going to explain. The Stanford experiment is different, though, isn't it? In the sense that here it's going to be a bit confusing, so I'm trying not to say it. Here we're rotating the whole lattice. The Stanford experiment, actually, they had each individual lattice site was elliptical, and it was going around. So it was like a rotation experiment with 4 or 5 atoms in a potential that just went round, but they just had multiple copies of that. So that's a sort of different thing. So what we'd actually need to do is to get close to the regime where we had the fractional quantum Hall effect states, without a lattice, and then you could impose a lattice and actually be helpful in increasing the interaction strength a bit, but you wouldn't sort of solve all your problems. Basically, as I say, we're in the sort of effectively a coupled-Josephson junction regime with hundreds of atoms per site. To be in the fractional quantum Hall effect regime, we have the same rotation frequency, but small numbers of atoms per site, quite dilute. And of course, other things that people have calculated a whole number of things, but for example, looking at the Mott insulator transition in a rotating lattice, then there are effects there as well. You actually see change in the transition, phase transition, depending on whether you've got frustration or not. The shifts, the phase transition around in terms of J over U.
Questions?
Can I just ask one more? I didn't understand why the critical rotation frequency went down. Is that just an effective mass effect then of the lattice? Or, when you explained the 4 Hz, that was basically without the lattice. But then when you turn on the lattice, you saw the critical rotation frequency went down, and then it somehow saturated at 1 Hz, so that didn't understand either of them.
Okay, the saturation at 1 Hz was purely experimental, that we didn't measure load on 1 Hz. So the 1 Hz, we didn't measure a lower frequency than 1 Hz. We could have actually. It was the frequency at which you could see vortices, and 1 Hz was the lowest we measured.
So why did it go down? Is that an effective mass effect?
No, because there's a difference there. In one case, you're stirring the BC, so the vortices are sort of created at the outside and they sort of move in. So that relies on that energetic argument that I described. So there is then a critical rotation frequency for which they'll energetically want to move towards us into the body of it. Whereas when we have a deep lattice, that argument's just not valid anymore. When we have a deep lattice, we actually, as we rotate, we create a phase on the wave function, which then when we release it, that phase is actually on the wave function. So there's no critical frequency for that. So even when we rotate at 1 Hz, we have enough of if we take enough plaquettes, we have a 2 pi phase shift, and we get a vortex within there. It's a completely different mechanism. Sorry, that's what I was trying to get over. That's the difference to having the deep lattice, where you actually essentially wind up the phase, and the shallow lattice, where it's more like stirring it and exciting excitations, which then, if they're energetically favourable, will move in.
And what was this then? What means deep? So it means the chemical potential of your lattice. So what do you mean with the deep? So it's always with your...
Yes, it's relative to the chemical potential. Yeah, so one is shallow, so the lattice is rotating underneath, as it were, inside the fluid, but atoms can sort of flow around the top.
Over the top. They have to enter from the outside. But if the lattice is deeper than the chemical potential, then you somehow increase.
Yeah, so deeper than the chemical potential is, that would be the atoms, and then they're just carried around with the lattice. Or if it's shallow, then the lattice is rotating underneath. The atoms can obviously just stir it, but the atoms can flow over the top, so that the whole thing is not dragged round. It's really stirring. In fact, it might be that actually it doesn't really do much in the middle, but as you get to the outside and the chemical potential drops, then these are the ones that are sort of carried round. And so the stirring probably is most effective at the edges. And that's, when you normally have if you have a BC I haven't actually got those slides here, but if you put a BC in elliptical potential and rotate it round, then the excitations happen, don't they? Well, you probably should see it in your simulations more than me, but excitations happen around the edge, and then they sort of work in to the middle.
When you go to shallow lattices, you describe your system still in the time binding approximation? Because we should, I think, I don't know.
I can't imagine. I mean, if it's smaller than the chemical potential, larger the chemical potential is like a kilohertz, around a kilohertz. If it's smaller than that, it's definitely not in the type binding regime.
Yeah, yeah, yeah.
And it's affecting mass or whatever.
Yeah.
Yeah, we should know.
Yeah, but you're talking about the single particle motion in the potential. I mean, that might be a model, I think, that's more relevant if there was very low filling factors. I mean, here we have very high filling, so I was really thinking of more of a
Yeah.
those condensate gross. I mean, for high filling, it's sort of and shallow lattice, and sort of some Gross-Pedievsky equation description.
I mean, your recoil is quite small as well, right? Your recoil is a few hundred hertz. It could actually be that you have there's a few recoil lattice. It could be that actually 4 kilohertz is in the type binding regime. So typically, when you have 2 to 3 recoil, you can apply type binding. It starts to become you get bound state.
No, it's okay. Yeah, this basically.